Good morning, September 21st. Yesterday was my day off, took a day off, and I believe I'm ready to start on problem 13. When I studied the section, it was really a revelation to me that one was able to prove that S and T generated the modular group, SL2. I've never been able to prove such a thing or even to imagine how it could be done. But these geometric arguments are really nice and well, it was a revelation to me. What more can I say? I have to repeat the same method with the Hecke group. And we have this fundamental domain, the Hecke group, yes. And we have to prove that it is generated by t squared and s. It's quite simple what to do. We can repeat the method of the book. So if you operate on Z, then the imaginary part and that must be squared. I just checked the formula. Yeah. And that means even it has a minimum distinct from naught, so which that changes, it has a minimum, which means that the imaginary part has a maximum. Actually, there will be an infinite number because when we have chosen C and D, we have an infinite number of possibilities for A and B. So we just choose one of them with maximum imaginary part. And then the idea is to work on S with it. And then the imaginary part of SS equals the imaginary part of Z divided by the modular of Z squared. And this means if this is less than unity, then the imaginary part is larger. Yeah, that's the idea I want to use on this fundamental domain. So it's in the unit circle, then the imaginary part will be larger. So there's a part out here that we don't use and a part here that we are missing. So the idea is obvious. We take the left part of the fundamental domain and move it to the right using t squared. So the fundamental domain we use for the proof will be this. And then so first we move our z into this strip using t squared, and if it's in this circle, in the interior of this circle, then we have the contradiction, so it must lie up here. And that means that by some combination, or by some element in the group generated by S and T, we can move it into here, and we're home. That was A. So we had to shuffle a little around with the fundamental domain. So let's go to B. That's gamma upper naught, or superior naught, generated by TST and T squared. T squared we know. So this is the group. For some reason I use the opposite here. That's of course the same map, and it maps to Z to, what was it, minus Z divided by Z plus 1. Minus Z plus 1. Oh, that was where the minus was, so we'll just correct it. And this guy, so again we can put it into the same strip as before, but then what action do we have here? So we multiply with the conjugate. Is that really sensible? Well, let's see what it gives. So units is okay, and then minus the real part of Z times 2, and then the norm of Z squared. I'm not sure this is nice at all. Let's look at the fundamental domain of gamma upper naught. this is the guy. You know what? I actually feel that it's much simpler if we take this part and shuffle it twice to the left using t squared, then we get a circle with center at -1. Put it into here. Interesting. So all of this was just confusion. What we need is to take the imaginary part of TST set equals the imaginary part of set what I need down here is the norm of 1 minus z squared, or z minus 1 squared. The norm of it squared. And we get that by multiplying with the conjugate. Oh, so it's actually the same thing. I was on the right track. This is real, so it's just the imaginary part of z. There we go again. We choose a set with maximal imaginary value, one of the infinite many, and shuffle it into this strip from -2 to 0, real part. And then if it lies in this circle with center at -1, we apply this guy to it, and then we'll get one with higher imaginary part contradicting the choice. That was B. C, that is gamma 2 itself. Well, I did have the full modular group of level 2 in my notes, and I have computed the matrix here. We don't care for the sign. That was a tennis friend, so now I have a match at 11 o'clock. I forgot this matrix. 2, 1. So we just call it M. And I've been working on these problems 2.5 years ago, and I found this this drawing, and I had to reformulate the fundamental domain to this to solve the problem, and therefore I recognize we have centers at plus minus 1/2, so we take out half. I don't really know this. I believe we should get z plus and half z. Well, let's see what we get. Imaginary part of mz equals 1/2. Imaginary part of, oh, it's a quarter of, this is real, so that's very weird. There's a mistake here, which I'll just find. I had to compute it again, and then I saw it was plus 1 in the denominator. So it should be plus 1 here. And plus 1 here. So it gives a quarter of the imaginary part of z divided by the norm of z plus 1/2 squared. And that means that if we can put it within this circle with center -1, minus 1/2 and radius 1/2 in here, then the imaginary part will be larger. But we can only put it within this strip because we only have t squared to operate on. So we need to take care of this strip as well. And then, of course, we need to find out how to transform this domain into this, but that should be pretty, I don't know, we'll look at it later. Well, I shall need another matrix, another operator, so that we get z minus 1/2 in the denominator. This doesn't seem to work. Nah. Nah. No luck with that. It all works on the other one here, and I can't get -1 there, apparently. Or does it matter what happens up here, basically? then it gets -3. Well. A little work I can do is to transform this into this domain. So first we map this part to the right side here, and then this piece, this is the unit circle with center in 1, so it has cusps 0 and 2, and then this has 0 and 2/3. And this one has -1 and -5/3. And we want to map them to just 0 and ±1. And in doing so, we hope that yes, what do we actually hope? We hope we'll get part of this circle and then the other one as well. I'll need to have it on papers, adjacent papers, when I look at it, and have the matrices as well on adjacent papers so we can see where the point maps. Hello, gentlemen. I couldn't sleep. It's 1 o'clock in the night. Then I wondered what I should do, and then I got the idea to work a little on this problem. Problem 13C, and hoped I would be able to solve it. The first problem was that I wanted to be able to change the fundamental domain to one of the two unit circles with center -½ and +½ and then map it to the upper part here. And I could do that with this matrix, and then I wondered which one should I use for the other circle. And that's actually easy, because it's just the inverse matrix. 1, 1, 0, minus 2. And that will of course give the norm of z minus 1 here, and it has to be the same, and there's no problem there. But I still needed to be able to transform the fundamental domain the way I showed you. We already have covered this part, so we have the rest here, which we need to map up until this part. So we must take the circle from 1 to 0, the circle from 0 to 2/3, and the line from 0 to infinity, and again the circle from 1 to 0, the circle from 1/3 to unity, and the line from 1/2 to infinity, and then see if we can map it over to, yeah, you know what. So I programmed it in Maple, and the operation on matrix on the in the complex plane, and tested it, and then G1, that gives 1/5, so that's not what we want. Let's try G2. That sounds much better. 0 goes to 0, 1/3 to 1, and 2/3 to minus 2. That's better. That's very good. And unity goes to minus 1. That's also very good. One half maps to infinity, and infinity to it's G2 to minus 1/2. So let's try to map the left hand side. Love to 2/3, go to, let's make that red. Blue's a better color. So, not, oh, this is 0 to minus 2. Yeah. And 0 to minus 1. We get that in both cases. And minus 1/2 up. So that means that covers this. And then green for the other one. 1 to 0 to minus 1 is this one. Oh, I should make it green as well. And 1 to minus 1. Oh, that's this guy. And minus 1 to, so that gives this. And that means that I have verified the fundamental domain I showed you, consisting of the two unit circles, and I've shown that the two matrices will map them above with a higher imaginary part. So that's my solution to part C. I think I solved problem 13D just before falling asleep last night. When I recorded, I was ready to repeat all the work of problem 13C, but then I realized that gamma of level 2 and gamma naught of level 4, they are isomorphic. With the isomorphism, meeting it to 2C and B halves D. That's the result of one of the former problems. Which one was it? That was problem 8. We have generators of gamma 2, namely t squared, and s t squared, or was it t minus squared they wrote? That's of course irrelevant. We take this guy as a generator of, just call it G. So the maps by the isomorphism here will of course generate gamma naught of level 4. That's this guy and this guy. So by the problem 8, these matrices generate gamma naught of level 4, and we just need to check that it's what they claim. This is T, of course. Yeah, and then this should be something like T to minus 4th. I said 4th, and there we go. That's exactly what it is. So 13D was trivial when all the hard work of 13C had been done. I'll be going on holiday for the next week, but when I come back, we carry on with the rest of the problems.